Hi, welcome all to my channel Computational Mechanical. Today we will look into the simplex method which is used in linear programming in industrial engineering. The subject is basically focused for the gate examination but is still open for people who are interested to understand the simplex problem, how it can be solved. So let's begin. Standard form of the simplex method, it is an iterative algebraic technique used to maximize or minimize our linear objective function subject to linear constraint. So in our problem, we have one objective function which just needs to be maximized or minimized based on the condition, and those are subject to some linear constraint. It moves from one vertex corner point of the feasible region to another, improving the objective function, and at each step until it finds the optimal solution. So in our problem, basically it will move from one corner point to another corner point in a feasible region, and it will improve my objective function, and we have to check whether the solution is optimum or not. It is a step-by-step procedure in which we proceed in a systematic manner from initial feasible solution with an improved solution until we reach the final optimum solution. So again, it's a step-by-step procedure which we have to follow, and we will put some initial feasible solution, then we have to move towards our improving the solution by checking whether the solution is optimum or not. This method also checks the corner points of a feasible region but in multi-dimensional depending upon the number of variable. So if variable is 3 or variable 4, then it will move into a multi-dimensional zone to find out whether our corner point is feasible or not. So let's look into the standard form of simplex. All the resource value for the given constraint should be non-negative. So this is my resource value. So this resource value should be non-negative. Second thing is, all the inequalities of a given constraint should be converted into equalities. So if this is my equation 3x1 plus x2 less than or equal to 40, then I need to convert into equality by adding a slack variable. Okay, now I convert it into the equality. Similarly, my second equation is 5x1 plus 2x2 greater than or equal to 45. Then I need to subtract my surplus variable. So if it's less than, then I need to add the slack variable. If it's greater than, then I need to add the surplus variable. So that's how we will make and convert into my equalities. My third point is, all the decision variable for objective function and constraint should be linear and non-negative. My x1, x2 should be linear and it should be non-negative. If we are having all this condition, then simplex can be solved. But when we can solve the simplex, we have the condition when number of variable is more than number of constraint or number of equation. So usually if I have four variable and I have two equation, let's suppose I have two equation. This can be solved by simplex method. How are we going to solve this? We are going to solve it by solving only two equation with two variable, and rest two variable we will put equal to 0. Okay, this is how we are going to proceed. Let's see. If n is greater than m, my number of variable is more than number of equation, then I will solve only for whatever I have number of equation, and rest I will put equal to 0, and those I called it as non-basic variable. Okay, then what I will do is, by basic variable I will got, then I will perform some calculation and will get the basic solution. Now the basic solution I will have to check for optimality. If all xj greater than or equal to 0, then this is my basic feasible solution. This is how I need to proceed. So there's one note that we solve only m equation with m variable, while rest non-basic variable are set equal to 0. This make our system solvable and each combination give us the corner point. If there are m equally constrained and n is number of variables and n is greater than m, then we need to put n minus m variable equal to 0, known as non-basic variable, and solve remaining m basic variable to give a basic solution. Basically, this step reduces the number of alternate solution whose maximum limit is given by NCM. This is a combination we can have if we solve all the variable, then we have n factorial by n minus m factorial by m factorial. This is a very large equation which we will get, but to reduce the time, this is a step we need to follow. So let's take one example and try to solve the problem. Solve the following LPP for maximization, where maximum z is given as 3x1 plus 2x2 plus 5x3. This is my objective function which I need to maximize or minimize, but in this problem it is maximization problem. And my constraint, I have given three constraints. I have given x1 plus 2x2 plus x3 less than equal to 430, 3x1 plus 2x2 less than equal to 460, and x1, x2 less than equal to 420. My first step is to convert all these into equalities. Since it is less than equal to 0, then I need to add the slack variable for all the equation, which I have done here. I have added s1, s2, and s3, and I have made this an equality equation. Now my maximum objective function, maximum z, also will get updated with this value. 3x1 plus 2x2 plus 5x3 plus I will have 0s1, 0s2, and 0s3. Okay, great. Now I have 6 variable, which is x1, x2, x3, s1, s2, s3, but I have only 3 equation, 1, 2, and 3. Now how I will need to solve? Now n minus m is 3 basically. Now 3 variable I need to put equal to 0, and rest I need to solve my equation. Let's suppose I'll start from the origin. My x1 equal to 0, x2 equal to 0, and x3 equal to 0. These are my non-basic variable. I'm starting from my origin. Now if I put this value in this equation, I will get s1, s2, and s3. And if I put those value in this equation, I will get the maximum value of z. So here I will get z value as 0. Okay, now I need to check the optimality, and to test and to check the optimality I need to make a table. So this is the table which we have to make to check the optimality. In the table, the first row is denoted as EI, which is nothing but profit coefficient, or the coefficient which are in objective function. These are the coefficient which I need to put. So 0, 0, 0 for S1. Since my all S1 are in my solution, so S1 are into my basis, S1, S2, and S3. On the first row, I have x1, x2, x3, s1, s2, s3. I need to put the coefficient which are there in my equation. For example, my first equation having 1, 2, 1, 1 and 0, 0. So 1, 2, 1, 1 and s2 and s3 are 0, 0. Similarly, I need to put for value of all. Similarly, if the second equation is 3, 0, 2, 0, 0, 1, and for third equation is 1, 1, 0, 0, 0, 1, which is equal to my BI is my current solution, which is equal to my 430, 460, and 420. 430, 460, and 420. Okay. We are okay with that so far. Now, the next step is I need to write the Cj. Cj is nothing but my coefficient of my objective function, which is here 325,000. 325,000. One thing to be noted in this table, whichever solution are in my basis, which are solution in my current solution, those variables should be forming my unit matrix. For example, if my S1, S2, S3 are in my solution, for S1, S2, S3 are making a unit matrix, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. My next step is to calculate Zj, which is nothing but the summation of Ei and Aij. So it's like 0 into 1 plus 0 into 3 plus 0 into 1, which is nothing but 0. Similarly, for all I need to calculate, I will get 0, 0, 0, 0, 0, 0 because all are multiplying with 0. Now I need to calculate delta j. Delta j is nothing but my Cj minus Zj. So it's nothing but 3 minus 0, 3, 2 minus 0, 2, 5 minus 0, 5, 0, 0, 0, 0, 0. So delta j, we call it as net evaluation row or net opportunity row. What it tells is, for example, for this value, so x1 we are getting 3. It means for 1 unit of x1 giving 3 rupees profit in my current solution. Similarly, for x3, it is saying that 1 unit of x3 give 5 rupees profit in my current solution. So this problem is for maximization. Then we need to find our maximum positive value from the delta j, and that would be my key column, or we are entering into that column. Okay, so here this is for maximization problem. Then we need to find out the maximum positive value. Then 5 is my maximum positive value, which means 1 unit of x3 gives me 5 rupees profit. So this would be my key column, which is entering column. And if it's for minimization problem, then we need to find out the most negative value to entering into the column. Okay, perfect. Now we have entering into the column x3. Now we need to find out which is my key element from first 2 3. Then what I do is I will calculate the replacement ratio, which is nothing but bi ratio of bi and aij. Okay, which is nothing but 430 by 1 is 430, 460 by 2 is 230, and 420 by 0 is infinite. In the replacement ratio, we have to find the minimum positive value, which is 230 in our case. This would be my entering row, and the intersection of these two row will give the key element, which is 2. Now we have to replace s2 by x3 here. Then we need to find out the value of objective function. This is we have to do for each iterative process and get the value of z. Let's proceed further. So positive value, the delta j positive value we are talking about. The positive value shows increase in value of if there will be any change in variable x1, x2, x3. Okay, this one x1, x2, x3. And 1 unit for maximum change will be the column n, hence 5 will be the maximum change for 1 unit of x. So 5 is the maximum, so we are entering into this column. Theta ij, for solution to be feasible and satisfy all the constraints, so we need to minimum and positive value in replacement ratio. Here we need to take the minimum value, and 230 is the minimum value we are entering. Now next step is calculate delta j value as the difference of cj minus zj, and it's termed as net evaluation row or net opportunity cost row. The value of delta j row gives the amount of increase or decrease in my objective function. If one unit represented by column head is brought into the current solution, a simplex table indicates the current solution to be optimum when all the values in delta j. So what we are saying is this will decide whether my solution is optimum or not. This delta j will decide. What is the condition? The condition is given here. The delta j should be negative or 0 when LPP is for maximization problem. Currently, my delta j is not 0 or not negative, it's positive, right? Positive and 0, which means it is not optimal. For maximization problem, my delta j should be 0 and negative. That is what written here. Okay, negative and 0 for maximization problem, and for minimization problem, it should be positive or 0. Okay, let's proceed ahead. The current problem is for maximization, so we need to select the highest positive value in delta j row and selected column head as an incoming variable. Great. Now, divide bi value from the corresponding element key column to get replacement ratio that we have already done. In this column, we select the minimum positive value and select the row is called the key row and the variable in the row as outgoing variable. The key element at the intersection of key column and key row is termed as the key element. So the intersection of this is basically a key element. My 2 is my key element. Now next procedure is, since I found out 2, then I need to make it as 1 and rest I need to make it 0. I need to perform my row and column operation. Since my x3 is now going into my current solution, which I've told earlier, whatever variable are coming into current solution, that matrices should make it a diagonal unity matrix. So I need to perform two operations. One, I need to divide second row by 2 to make it 1, and I need to subtract r1 minus r2 to get this down 0, and this 0 is already there. So I will make this a unity matrix. Okay. So a key column, key element is converted into unity by multiplying or dividing key row by a common multiplying factor. All the elements in the key column are made 0 except the key element, which will be unity. This is done by adding or subtracting the proper multiple of the key row from other row in the new table as an outgoing variable. Again, we have to perform the row and column operation. So my first operation will be r2 divided by r by 2. So I will perform this operation, this row, I will divide whole equation, I will divide by 2. For example, if you go up, so this would be 3 by 2, 0, 1, 0, 1 by 2, 0. And this will be 430 by 2. So 3 by 2, 0, 1, 0, 1 by 2, 0, and 230, infinity. My second operation is r1 minus r2. Okay. So r1 is nothing but this one. So this r1 I need to minus with R2, which is this one, to get my new R1 value. And R2 we have already 0 here, so there's no worry. Now, since we have applied this operation, I have applied all the rows in a column operation. Now, my new equation suggests that my S1 value is 200, X3 is 230, and S3 is 420. And rest X1, X2 are 0, and S2 is also 0. Now, I will put all this value into my Z. I will get 1150 value. Now, I need to check whether this is my optimum solution or not. For that, I need to perform again this theory. Cj is again objective function 325000. My Zj is nothing but ei minus xi. So 0 into 1 by 2, 5 into 3 by 2, 0 into 1. So what I will get is 15 by 2. Similarly, I need to do it for second case. 0 into 0, 0, 5 into 0, 0 into 0. I get 0. Similarly, for all, I need to calculate. Now, my delta j is Cj minus Zj. What I will get is minus 2, 2, 0, 0, minus 5 by 2, 0. For maximization problem, my delta j should be negative or 0. But here I have a value of 2, which is positive value, which means the current solution is not optimum. There is one more iteration I need to go ahead with. So this would be my incoming variable. Now I need to divide theta j. I need to find out theta j, which is bi, by x2. And what I will get is 200 by 2, which is 100. 200 by 0, infinite. 420 by 1 is 420. Now I need to have the value of minimum positive value, which is your first one. Which means if I do an intersection of this, I will get, would be my key element, which is 2. Okay. Now what I have to do is, again, I have to perform the row and column operation to make this as 1. And this is 0 is fine. Again, I need to make 1 as 0 here. I need to make a change. So my row operation is R1 is nothing but R1 by 2. And my second operation is nothing but R3 is R3 minus R1. Let's go ahead. So as I already written here, R1 we have to change by R1 by 2. So basically if I go up, I will see this equation R1 by 2, which is 1 by 4. This is 1, 0 by 2, 0. 1 by 2 is 1 by 2. Minus 1 by 2 by 2 is 1 by 4. Like that, I have calculated my next equation. That's table. Similarly, x3 I don't need to make change because my x2 is already 0 here. Okay. This one I need to change because this one I need to convert as a 0. So what I will do is R3 is nothing but this R3 minus my R1. Okay. So this row I need to subtract from this row. Okay. What I will get is nothing but 5 by 4, 0, 0, minus 1 by 2, 1 by 4, 1, and 320. Okay. So now if you see, my x2 has come into basis, which means my x2 should be 1, 0, 0. My x3 has come into my basis, which means 0, 1, 0. And s3 is come into my basis, which means s3 is 0, 0, 1. Right? So I'm making one unity matrix. Now I have to check the optimality. So my x2 is equal to 100, x3 equal to 230, s3 equal to 320, and rest 3 variable are 0. So I will get the value of z is 1350, which is 200 more than my previous solution. Now this is my third feasible solution. I need to check for the optimality. Now I will calculate the Cj, which is 325000 from the objective function. Now I'll get Zj. Zj is nothing but 2 into 1 by 4 plus 5 into 3 by 2 plus 0 into 5 by 4. I will get 7. Similarly, I need to calculate Zj for all the row. And the last is the delta j. Delta j is nothing but Cj minus Zj, which is 3 minus 7 minus 4, 2 by 2 0, 5 by 5 0, 1 minus 1 minus 2 minus 3. Now, if you see my delta j, it is 0 and negative, which means the value which you have calculated, 1350, is my optimum solution. So for the equation we got, our maximum z value is 1350 based on we did the optimality check. I hope you liked my video. For Simplex method, do subscribe my channel Computational Mechanical and do support my video. I will be coming up with more interesting topics on whole mechanical engineering